So far, we have talked about applying Newton's second law with respect to an inertial reference frame. The question comes about what happens if the reference frame is accelerating? Is it possible to apply Newton's second law? Up to this point, we've been saying that is not possible, but technically the answer is yes, provided you make some adjustments. And so the purpose of this video is to understand how we can apply Newton's second law to an accelerating reference frame. So in this picture, with the accelerating rocket problem, so we have the one reference frame that's attached to the rocket. Let me put this in slideshow mode. All right, so one reference frame that's attached to the rocket, which is shown here with the subscripts A for accelerating, and the other reference frame attached to the ground, which is the non-accelerating or the inertial reference frame. So if you take Newton's second law in the XYZ attached to the ground or the inertial reference frame, this is what it looks like, ddt of the integral dv. This is the integral over the volume, and this is the integral of the total momentum, and then this is the integral over the control surface, and then I have vrel dot dA equals sum of all the forces acting on the control volume. Let's label this as equation 1. Now, this is my accelerating reference frame, and if I have the velocity in the accelerating reference frame xa, ya, za, if I add the velocity of the accelerating reference frame itself, right? So in other words, this rocket is moving at a certain velocity, which would be the velocity of the accelerating reference frame. If I add it to the velocity of the attached reference frame attached to the rocket, this is going to give me the velocity with respect to my inertial reference frame that is attached to the ground, right? So this is simply the definition, if you will, of relative velocity and absolute velocity, right? So this is the velocity as seen by an observer attached to the ground. This is the velocity as seen by an observer attached to the accelerating rocket. Provided I add the velocity of the accelerating rocket, that's going to give me the velocity as seen by an observer attached to the ground. So if I make this substitution into equation 1, this is what I'm going to get. So wherever in equation 1 I had a v little xyz, I have replaced that with a little xa, ya, za. And then I have this additional term which needs to account for the presence of the accelerating reference frame term in this equation. Equals sum of all the forces. All right, so I have 2 terms here. Now that's become 4 terms here because this velocity is made up of 2 terms, right? So if I make the substitution, this is what I end up getting. Let's label them as terms A, B, C, and D. All right, so I'm going to focus on term C first. So this term right here. All right, so focusing on term C, if the entire rocket is moving at the speed VARF, so every piece of mass sitting inside the rocket is moving at the same speed, which is the velocity of the rocket. that's the assumption we are making, then essentially term C, I can write it in the following manner. I can write that as ddt of mcv times velocity of the accelerating reference frame, right? So in other words, this velocity I can pull out of my integration, and then what's left over is simply the mass of the rocket, or mass of the control volume in this case. And this term, I can now write this in as two terms, the product of two terms. The first one is mcv times dvarf dt plus varf dmcv dt, right? This just comes from the product rule in calculus. If I look at term D, which is the integral over the control surface, and just looking at the accelerating reference frame component of the total velocity. So VARF is the velocity of the reference frame. I can bring this out of my integration. So I can take this out of my integration in term D. And if I did that, I'm left with the integral over the control surface of rho v rel dA. Okay. And then, so if I take terms C and D, combine them together, right? So term C, I got this, and term D, I got this. So if I combine those two together, I'm going to get mcv plus velocity of the accelerating reference frame times dmcv dt, right? This is the sum of, this is the product rule, plus the term right above that I've got, the ARF, integral of rho VRL dot dA. All right, so what can I do now? I can write this as mcv. So I'll copy the first term on the right hand side as it is. Now the ARF is common to two terms, so I'm going to factor that out. And what I'm left inside the parentheses, dmcv dt plus integral rho VRL dot dA. We recognize that this is nothing but conservation of mass statement, which means this is precisely equal to 0, right? So that makes things simple. So if I go back and take into account term C and D that I simplified this way, and go back and put this into, let's label this equation over here as equation 2. If I put all this together, what I'm going to get is the following. dV plus the integral over the control surface rho this is xa ya za VRL dot over dA equals sum of all the forces acting on the control volume, and the one term that's left over, I'm going to move it to the right hand side. Right, so this is the term that was left over here, which I moved to the right hand side, and this term, remember, becomes 0. So that is the term that is appearing on the right hand side over here. Right, so let's label this as equation 3. And if I look at equation 3, it looks exactly like what I would write down Newton's second law for with respect to the inertial reference frame. I'd have the rate of change of momentum inside my control volume with all velocities measured with respect to my reference frame. I have the outflow minus inflow momentum across the control surface with the velocities for computing momentum measured with respect to my reference frame, equal sum of all the forces. The only distinction now is the reference frame is an accelerating reference frame, and so to account for that accelerating reference frame, I have this extra term minus mcv dv arf dt. So if I did this, then I get I'm able to now apply Newton's second law directly to an accelerating reference frame, right? So the only requirement is this extra term be added to the right hand side. So I'm going to think of this as the modified Newton's second law in this case. Now let's summarize this equation on the next slide and start thinking about applying this form of the equation, right? This, I would call this a modified Newton's second law, if you will, where this extra term appears on the right hand side. This form of this equation to this accelerating rocket problem. Let's go back and look at it, right? So I'm going to label this as term A and term B over here. So on the left hand side, in this new reference frame, term A is reasonable to make the assumption is equal to 0. So if I'm viewing this from a reference frame moving with the rocket, remember my reference frame is now attached to the rocket, really there's no change in momentum, right? So there's really no change in momentum, and so that's why this term is equal to 0. If I take term B, on the other hand, this is simply equal to the there's only outflow taking place right at this exit station. So this is simply going to be m dot E times negative VE. So this is the velocity with which the fluid leaves the rocket as observed by an observer sitting on the rocket. So that is m dot E, and it's pointing in the negative Z direction. So that's why it's negative V sub B. And this has to equal, on the right hand side, we got mCV and then we got mCV, in this case dVz dt. This is simply the velocity of the rocket. So if I solve for dVz dt from here, I get m dot E VE over mCV, right? So I'm going to solve for this term, move everything else over to the other side of the equation, and then minus G. Okay. So this is simply minus G plus m dot E VE. In the denominator, we previously worked that out as mCV of 0 minus m dot E times T, right? So this is exactly the same equation we got as before, where previously we had applied this to a reference frame attached to the ground. And you can see now with the reference frame attached to the rocket itself, provided you take this extra term into account, you're going to get the same result. So we're going to summarize Newton's second law applied to an accelerating reference frame in this manner. It looks very similar to Newton's second law applied to a stationary reference frame, but the fact that this accelerating reference frame is indicated by the fact that we have this subscript A for acceleration. All you need to do is add this extra term with a negative sign, mass of the control volume times the acceleration of the control volume itself. So this is essentially equation 3.45 in Frank and White's book, 8th edition.